That's me up there. I'm a cloud solutions architect for media and entertainment, and at Google. I'm based in Los Angeles, and I've worked with some of the people at this show. I spent 20 years working in visual effects on the pipeline side, and on the creative side, and on the effects side. And when I was a pipeline TD, my job was to make things work and fix things that break. But now my job is to make things work on the cloud and fix them when they break on the cloud. And I've been at Google for about 3 years, and I've worked with a bunch of companies that are render specific, but there's a lot of other workloads. We're going to talk about that today. I'm going to try to go as fast as possible through the first section, which is not super tech oriented, but I need to give you a setup so that you understand what we're looking at and what's possible on the cloud. And because we're going to talk about something called Virtual Studio. I'm going to show how to run distributed renders in a bunch of different ways, in a few different ways. And I'm also going to introduce a new way that we came up with recently that is sort of a bit of a breakthrough, which I'll sort of explain in a bit. But what is happening on the cloud right now, just a little primer, in media and entertainment. And that sort of falls under, there's a bunch of different sort of what we call verticals falls under media and entertainment. But when you think about companies, it's not just rendering. There's also things like Netflix and live streaming and or Hulu or Fubo TV. Those are all, some of those customers actually run on GCP. And then they also do something called transcoding. A lot of these workloads involve GPUs as well. So I'm going to speak about NVIDIA GPUs quite extensively throughout this talk. But transcoding is basically taking a movie file format from one format, converting it to a different format. But you'd be surprised at how much work there is out there that's needed to do that. There's also something called intelligent content discovery, where you've got an archive of images or videos, and you use machine learning to tag and categorize those assets and provide you like a searchable database. There's a lot of activity going on in those areas. And then rendering is not just rendering, but it's any type of compute workload on the cloud. And compute could be fluid dynamic simulations or CFD simulations, rendering in real time or rendering in offline, and also customers like the big VFX houses, they're rendering in this hybrid mode where they have their own on-prem render farm, but they want to send some stuff to the cloud. And then there's Virtual Studio at the other end of the spectrum. Virtual Studio is, we're going to review that in a second. But these are the two workloads that we're going to focus on today. And I want to sort of give you a primer on Virtual Studio and what that entails. And there's actually some videos on YouTube you could watch of me giving a bigger breakdown of how Virtual Studio works, but I want to talk about what you're looking at here and speak about the pillars of what Virtual Studio is. By the way, this whole talk is a testament to the portability of all of this because I'm running off of my hotspot on my phone. So apologies because the internet here is a little bit spotty, but just to show you what's possible just from your own Wi-Fi or your own 4G connection, not even LTE. So Virtual Studio is composed of a bunch of different blocks. First thing, connecting to the cloud. You can connect in a bunch of different ways. Right now we're connected over public internet, but there's all these enterprise grade things that you can connect with, and you need not a substantial amount of bandwidth, but you need a consistent amount of bandwidth in order to connect to the cloud if you're going to have a virtual workstation on the cloud. And then we have this notion of brokering connections. How do you connect to a machine on the cloud? You're going to see me dial into a machine that is located in the Netherlands. And to do that, you need something called a cloud connector, which essentially takes in an initial connection and brokers the authentication to other authentication proxies that might be dialing into your Active Directory service, sends a push notification to your mobile phone, you click a button on your phone, and then it grants you access to the resources. So that's sort of the proper way to do things. Right now, I'm just going to connect directly, but that's not important. One of the most important factors, though, is the display protocol, how you're viewing the desktop streaming from the remote machine. And I know there's some discussion out there of which one is best, but we've been working with Teradici PC over IP for a long time. And I know people have been working with PC over IP for more than 10, 15 years just because they existed well before cloud, first on hardware, but now in software. But the important things about display protocol is color accuracy and the ability to resolve to lossless and high-res monitors. If you want to have dual 4Ks at 60 hertz, you've got to really think about what kind of bandwidth is required, and what kind of equipment you're going to need. And then there's this notion of how do you create the resources and how do you create the machines on the cloud. There's provisioning, and that's basically taking a bunch of users and taking a bunch of resources and assigning them one-to-one or assign multiple resources to a single user. And then you've got to define, what kind of user are they? Are they an effects artist? Are they an animator? Are they a lighter? And how many GPUs do they need? How many CPUs? How much RAM? And there's a whole bunch of different partners that we use for provisioning resources, and there's also some other prototypes that we're working on as well. And then storage. If you've got a bunch of users, tens or hundreds or thousands of users on the cloud, how are they all going to share the same assets and have access to the same, what everybody just expects is pretty standard, just a shared NFS file server or Samba file server. And what if they're located in different parts of the world? How do you synchronize those? So there's a lot of questions around that. And finally, monitoring of these resources is really easy on the cloud because there's all these mechanisms built in to access the things like logs and memory pressure and load on the machine and everything. And you'll see some of that in a little bit. So also, and I'll talk about the costs of what you're looking at later on, but there are a lot of things to think about. And that's actually one of the things that people are kind of afraid of when it comes to moving to the cloud. And that's, they don't know, it's an open-ended question as to how much things will cost. And because on-prem, you basically write a check for something, and then after that, it's free, right? But people don't take into account electricity and air conditioning and maintaining and fixing things that break. But you also have to add in, think about things like bandwidth and cloud storage and synchronization and getting your data up into the cloud and then getting the signal back down. Security is another big factor that we deal with on a day-to-day basis because we're closely partnered with the big 6 Hollywood studios for security audits and compliance, and there's a whole deep discussion that I don't want to go into on that, but if you, throughout this, my slide deck, there's these QR codes. If you take a photo of it and you can blow it up and you could scan it, you can go to the URL that's associated with, but there's a lot of stuff going on in terms of security, including what's called the Trusted Partner Network. If anybody here works for a big VFX studio, you might have heard rumblings around this. This is a new certification that's going to be coming, I think, towards the end of the year, but we'll have to see. And that's going to basically allow you to get a certification to say, I am compliant with the requirements for Disney and Sony and Paramount, et cetera, et cetera. Getting closer to the more techie part of things, there's a lot of GPUs available on Google Cloud. And Stephen Parker gave a pretty amazing talk earlier. He alluded to the Turing platform, which is this T4 that you see on the right-hand side. The T4s do support RTX. They have RT cores, as well as the tensor cores on board. So those are available in different configurations. And on cloud, you can attach more than one GPU to a workstation, and you can scale it up and down as you see fit. So if the beginning of the day, you only need like a small P4, for example, which is an inexpensive workstation class card, and then later on you want to do some heavy GPU rendering, you could crank it up to, you could add 4 GPUs or 8 V100s if you want. And there's all sorts of different workloads around visualization. No time to get into that because I want to focus on some of the meat of the main course of this presentation. So we're talking about distributed rendering, and I've done a lot of run a lot of demos in the last couple of years about distributed rendering, and try to talk about some of the problems that we encounter and what not only cloud, but also just a different way of thinking about distributed rendering brings you. And that's, what are the problems that people are facing right now? And I've talked to a lot of customers that are frustrated with how they can deploy distributed rendering on-prem. And that's basically is that, number one, they have a limited amount of resources that are usually reserved for offline rendering, right? And also, if they're as opposed to interactive rendering. The way that I frame distributed rendering is there are offline renders where you render a single frame across multiple machines, or there's interactive IPR rendering where you've got a bunch of IP addresses that you can farm out your render work to. And those two are kind of orthogonal, like they're always butting up against each other because you might want to reserve those IPs for render jobs that are in your render farm. The other big factor is it's really expensive to integrate GPUs into your on-prem render farm, and GPU rendering is obviously a big topic today. And they're expensive to operate. They run really hot, so you have to add more cooling, et cetera, et cetera. And also your on-prem render farm needs to be close to you, right? The latency needs to be low enough. So if you have a co-location facility that is, a few hundred miles away, and your network is not capable of transmitting the data in a low enough latency, your distributed render might not even work. So it's sort of locked to your physical location. And finally, there's also it's very noisy, right? If you add a whole bunch of machines and you get a bunch of users, artists using those render workers, you're going to use up a lot of bandwidth. There's going to be a lot of traffic on your network, and that might hit the rest of your network in terms of what your render farm can handle, et cetera, et cetera. So, and this is kind of, when I'm going to say on-prem a lot, and I know that it's sort of a silly cloud term, but it's on premises, which I mean your own infrastructure, and this is infrastructure that you own. And this is an example of what an on-prem infrastructure might look like, where you've got just a whole mess of render nodes that you can connect to that are always running. You never shut them down. You have to pay for their electricity. You have to have IT staff and systems hardware staff to keep them running and fix them if they break, and they depreciate over time, and you have to replace them after a certain number of years, after their lifespan. But these are some sort of common things. I'm going to go through a bunch of architectural diagrams here. But there are a bunch of common things that you might see in an on-prem deployment, and that's you've got your artist workstations. They have some sort of a broker or a queue manager to say, these machines are reserved for this user, and this is a distributed render workload, by the way. This is not this could be an offline render as well, but the broker is basically reserving machines for a particular task. They're also connecting to a license server, and they're hitting the license server. And if you're running a Chaos Group license server, then it's going to reach out into cloud if you're using those types of licenses. And then obviously you need some sort of big heavy-duty file system, this network attached server. And this is what people have historically done. And this presentation, I like to think of it as like the past, the present, and the future. And this applies to what I would say the past, because people are now moving over to cloud, which is sort of the present. But let's talk about, just finish off and think about what the challenges, the pros and cons are of on-premises. And that's, you've got 100% control over your image and your network and the hardware and everything. But the cons is you also have 100% control over the hardware and image in the network. So you're responsible for maintaining and fixing it. And like I said before, you got to pay for electricity, and security is an issue, because if you don't have security experts, then somebody could even walk in and steal a hard drive or a server and walk out. And these are things that sort of on-prem facility staff need to think about. So one of the important points here that I'm going to go through these different pros, cons, and use cases for different workloads is the location is important. And this is helpful if your location, your connectivity is scarce, but power is abundant. So let's say a perfect example is Weta, right? Weta built out their own render farm, and one of the biggest render farms in the world. I think they had 120,000 cores at one point. But they historically have been very isolated from the rest of the world, and they don't have big connectivity and big bandwidth to the mainland, right? They're in New Zealand, and they're many hundreds of milliseconds away from the nearest data center. Historically, things have changed, but power is abundant there. Obviously, they have a lot of access to power. But let's say you're filming a shoot in the middle of the desert, in the middle of the desert, the U.S. or in Africa, or even out on a platform of a ship. If you're working on an oil rig, for example, and you want to, we actually have a lot of customers who are in oil and gas who do these computational fluid dynamic simulations to determine where to drill for oil. And they have to run these data sets that are terabytes in size, and they take hours and hours, sometimes days to load. Like there's these data sets that I learned about at GTC that take like 8 hours to load, just to load into memory. And there's no way you could do that on-prem. So this is one of the limitations here, and the use case doesn't fall within there. But this is sort of what we've looked at for the last 20 or so years. So what is the solution? Why am I here? And obviously I work for Google, so of course the solution is the cloud. But I'm going to tell you why. The first iteration of distributed rendering that I was playing with in the last couple of years is the notion of a managed instance group, and this is what the architecture would look like. And actually, if you look at Total Chaos from last year, I did a talk that reviews and I do a demo in this realm, and I talk about the managed instance group and how it can scale up and scale down. And this is helpful, and it's a very efficient and very powerful way to do distributed rendering, in that you've got your virtual workstation, which I'm going to show you in a second, and then you've got this notion of a managed instance group. And a managed instance group on GCP is a collection of workers that are all identical, and they could be deployed and scaled up and scaled down somewhat quickly. And they're all based on one or a few images. So basically, you create a disk image that's exactly as you want. If it's a render worker, you're just going to, it could be a Windows or a Linux image, with all the software and the licensing hooks and everything that you need. And then you create a snapshot of that, and then you can apply that snapshot to what's called a template. And a template is a configuration of a worker. So your worker is how many CPUs and how much RAM and how much disk and how many GPUs if you want to attach GPUs. So all that is customizable, but the managed instance group is based on a single sort of template implementation of that. So with a managed instance group, you could scale it up, from 1 to, I think the maximum number is 2,000 nodes per group. And each of those will get a unique IP address. And if you plug those IP addresses into your distributed rendering, your DR, the UI, the V-Ray UI, then all those machines will just start working as your distributed render service. V-Ray DR is surprisingly efficient at synchronization, and even if you've got a Windows machine and you've got Linux machines that are in the cloud, it transposes all the file paths and everything, and it just works really well. If you have a shared file system that's attached to both your virtual workstation and your managed instance group, so each worker in the managed instance group will mount that same NFS path, or Samba path, but NFS is preferable, then they don't have to synchronize the data, and they'll just read the same file path that the distributed render, that the virtual workstation is reading, which is very much like your on-prem setup, right? Like everybody mounts the projects directory or the tools directory or whatever, and you can mount as much or as many or as few NFS paths as you want. So managed instance group is super handy. The limitations, though, is that this is the most important point here. The biggest limitation is that it's one virtual machine, means one IP address, and one user can use that machine. So that can create substantial costs if you have one user who isn't taking care of their group, and they scale up to 100 workers and they leave it running overnight or something, even though they've stopped rendering. And that means you got to monitor these groups, and there's many different mechanisms and interfaces and toolkits, API, SDKs to build these monitoring dashboards and these alerts and event handlers that could say, this group has been idle for X number of minutes. Do you want to shut it down, or push it to you basically this is what your render wranglers are going to take care of. So it requires monitoring either by a human or by some sort of higher level API. There's also this notion of auto scaling, and auto scaling is more for, in the cloud world, web services auto scale. So let's say you've got a service that runs on the cloud, and this is totally outside of rendering or anything. You've got a service that runs on the cloud, and you've got a big announcement, and there's tens of thousands of people click the link and they go and they access this tool or something. Well, if you had that tool running on the cloud on a single virtual machine or a few virtual machines, the thing would fall over, and because there would just be too many requests and too much compute required to feed all these users. And auto scaling will track the CPU load or the memory load or the disk load, a bunch of different metrics, and it can scale up a managed instance group as it sees fit until it reaches equilibrium. So if you say auto scale at 80% CPU load, for example, and keep adding machines until it's reached that equilibrium, it'll do that automatically. And then when all the network traffic dies back down, it'll scale back down. These machines can be scaled up and down pretty quickly, and as long as it takes a virtual machine to deploy, which with a GPU that's around, I think it's around 40 or 50 seconds these days, on GCP at least. Without a GPU, it's a little faster. So auto scaling is super handy, but it's some sort of a higher level control that it may not necessarily be useful in a render workload, because basically rendering is most efficient if everything is at 100%. So you can't really say if it's at 80%, keep adding machines, because you're gonna keep chasing your tail, and it's just gonna scale up to the max. You could set a maximum size of the group, so don't be afraid. So there are a lot of companies that are using this already. Customers that I've worked with that I've shown this to them, they're like, yeah, it's pretty simple to deploy. And again, there's some videos online of me showing how to deploy it, and there's some tutorials online that talk about how to do it. So it's pretty standard, and also you can take advantage of what's called preemptible VMs. Preemptible machines, if you're familiar with cloud, they are sold off as excess capacity. So there's always excess capacity. You know, a data center is never 100% occupied, and we sell these machines off at 80% off of the cost. So if a machine is $1 an hour, a preemptible will be 20 cents an hour. And they're super handy for rendering workloads, because the preemptible machines, we sell them to you at a much lower cost, but with the agreement that there's a 10 to 15% chance that they'll be taken back into the pool, the standard pool of resources. And you're only given a 30-second window of opportunity to move that workload or to kill it and restart it somewhere else. But for render workloads, it could just be treated like a failed frame. Obviously, for offline individual frame renders, that makes sense. But if you're doing distributed render, either interactive or frame render, you're going to have to, and one of the machines drops out. If you're doing progressive rendering, that I'm sure this group could tell me better than I know, than I could speak about, how the progressive renderer fills in and accounts for lost resources. I know that when I've done this before and machines have dropped out, the progressive renderer just sort of solves it and just uses fewer resources. So it's pretty, the V-Ray engine to do that is pretty dynamic. So preemptibles are actually a great way to save money and deploy that across different regions. And that's another thing here, is that you can access resources anywhere in the world. You can create on cloud a set of machines that is in North America or Europe or Asia. We have a data center in, I don't have a map unfortunately on this slide deck, but we have a data center in Sydney, Australia, for example. So you want to deploy as whatever's closest possible. I've deployed in the closest region with the GPUs that I wanted, which is in the Netherlands, which I think is around a 10 or 11 millisecond ping time. And that's important for reasons that I won't go into here. The future of what we're talking about today is deploying in a different way, and that's using Kubernetes. Has anybody here who heard of Kubernetes containerized? Awesome, you guys are all awesome. And feel free to call me out on things that I don't explain fully. But myself and a colleague came up with the notion of GPU attached Kubernetes clusters, and that's kind of historically been difficult because on cloud at least, and on-prem is different, but on cloud you can't share a GPU, right? Like I said earlier, you've got one VM, one IP address, and all the resources that are associated with that VM are sort of locked to the user that is accessing it. So let's say the simplest case is you have a VM, and it's not in a group or anything, it's just standing on its own, and you run V-Ray server, like the V-Ray command with -server over port 2027, everybody's familiar with that. And I take that IP address and I connect to it as a distributed render server, and it starts working and starts feeding me data. Somebody else goes and takes that IP address and tries to connect to it. It's impossible. They can't, because I've already locked that IP address, and If that port is already occupied for that IP address, V-Ray server will just sort of kick it back and say can't access or connection timed out or something. So that's historically been the problem with these non-containerized workloads. So what I'm going to show you here today is how we've built out a clustered, scalable distributed render service on GCP. It's a service that you run. It's not a service that we offer yet, but I'm going to show you how it's constructed and how we built it. So what's happening is you've got, and I think this deck steps through this, yeah. There's this notion of the cluster, the nodes, and the pods, if you're not familiar with containerization. And the cool thing about Kubernetes is that these pods, which that's where the V-Ray server command will run, or the V-Ray server, the port will open. Those pods deploy in seconds, like 5 to 10 seconds, if you've got a host already running. And you could have as many or as few pods on a host as you want, and each pod can be assigned to a different user. And I'll show you that in a second. It's also much more programmatic to deploy these things. We've constructed this with Terraform, not TensorFlow, Terraform and Docker, and everything's containerized such that you can make slight modifications. For example, the host type that I've chosen is, I think, only 8 CPUs, and it's got a lot of RAM. It's got 64 gigs of RAM, and it's got 2 GPUs attached to each host. If I wanted to add, if I wanted to have 4 GPUs per host, I would just go into a config file, change the 2 to a 4, and update the Terraform config and push it out, and it just, the next time a host spins up, it would have 4 GPUs instead of 2. It's super easy. Everything is isolated, which is really handy as well, because now you've basically built and containerized. This is the focus of containerization, is that in this Ubuntu container, for example, you're running only V-Ray, nothing else. You're running V-Ray, and it's talking to a licensed server, and that's it. So these things are completely separate from something else that you might be running on the same cluster. You can also deploy across zones, which is really handy for data centers are separated into regions and zones. So, for example, I'm using the Europe West 4 region, which is in the Netherlands. And in that region, there's 3 zones, A, B, and C. And you could spread your Kubernetes cluster across those 3 zones to get different resources. Like there might be P4s available in one region, in one zone, and T4 is available in another one. So you could sort of mix and match, and also to get different capacities, right? So depending on where you operate, there might be lower capacity in one zone and higher capacity in another. So you could expand to different zones. You can run preemptible hosts as well. Obviously, you need to take that into account and tell Kubernetes what to do when a host drops out. And the resources can be shared. That's the important thing. The cons, it's more complex, admittedly, to set this up. But once you understand the configuration and the workload, it makes a lot of sense. And obviously, you need somebody at your company who's got experience with DevOps. You need a DevOps team to be able to deploy and monitor this and figure it out, and to be able to address issues as they come up. So let me again, we're running off my phone. So I am on a Mac, and I'm running the Teradici. Just brighten my monitor a bit. I'm running the Teradici PC over IP client, the software client, and I'm going to connect to a machine that is just an IP address. It's a public IP address. I don't have any fancy brokerage going or anything, so I'm just connecting directly. Let me just log in here. And Teradici, we recommend around a 10 megabits, 10 Mbps connection per user for a dual HD setup, a dual HD monitor setup. The requirements can vary a little bit here and there. But I'm running Maya, and it's actually pretty interactive. I don't have a real mouse here. I got my trackpad, so I'm not going to be able to do much. But I've got this simulation that, again, you might have seen in some videos I've shown before. This was actually done for the LA data center launch back last June. But I've built this little tool called this V-Ray DR Cluster Manager, and right now I have nothing running. But if I wanted to deploy like 6 nodes, I just type in. Can you see that? Yeah, I just type in the number 6 and populate the IPs, and they're going to start populating. So it's spinning up believe it's spinning up nodes right now. So let's actually have a quick look at, escape out of here. Let's have a quick look at the cluster. So this is the GCP console, and in here I'm in the Kubernetes engine section of it, and I can look at the cluster itself, and I could see all sorts of information and look at how many nodes are my. So I've only have a single node here right now, and it is in the process of spinning up multiple nodes. Once the nodes are spun up, I can track them and see which pods are running on these nodes. By the way, when after Total Chaos is over and I get back to the States and I build out this tutorial, we'll be open sourcing this so everybody can have access to this tutorial that you can run on Cloud Shell, which I'm showing right here. I'm not going to go into too deep, but there's this, we have this mechanism so that you could run through these tutorials. You just basically click a button and it launches this section here. And for example, I'm going to go back to the beginning of the tutorial and do things like, first you set your project, and it's next 19 render demo. And then you can just click through and run these commands one by one, and you can sort of explore and understand what it's doing, right? So here, for example, it installs Terraform. By the way, I'm going to back up again. I'm running in what's called Cloud Shell, which is an instance that's spun up on the cloud for you when you log into the GCP console. It is a machine that exists in the cloud somewhere. It doesn't really matter where, and it's your home directory in the cloud. So if you close and reconnect from a different machine, or as long as you're logged in as yourself, as your user, I'm logged in as my user here, you will get the same Cloud Shell environment. So in all these cases, we're going to do things like authenticate and deploy different Terraform scripts and everything. And like I was saying here, like Terraform apply, like if I wanted to change these machines to different numbers. So let's go back and look at nodes. We still only have that one node. I'm trying to request more nodes, but it takes a second to. Let me go back and issue some commands here. So we could do things like cube control, but really people call it kubectl, get pods, right? And the very first time it takes a second to just authenticate, but remembering this is running over my phone. I do need to authenticate, so let's go back and we'll set project and yes, everybody hide your eyes. But you'll get the same thing too, because this is a good lesson in how authentication happens. And I'm going to allow, and then it gives me this hash that I then just paste in, and now I'm authenticated. So now I should be able to run get pods. What is going on here? What? The cloud crashed. That's interesting. All right, let me just try to do that again. This is interesting. Let's go back to Maya and we'll see if we've spun up any further. There we are. So now the IPs are populating. And every time I click repopulate IPs, it is going in, and these are a bunch of Python scripts that I wrote that I'll share with you. It's going back in and it's updating the IP addresses of the distributed rendering, the XML file, right? So as this node count grows, I think there's probably a certain amount of nodes. I don't know what's going on there, but I've actually got a movie file here that I recorded earlier, just in case this happened. But there we go. So now we've got more nodes deployed. All right. So let's go and update again. Okay. So we got 3 nodes, and we're just going to turn on V-Ray IPR. And unfortunately, I can't connect to my. It's interesting why it's not connecting. Let me try. I'm just going to open a new shell. So you could also, every new shell you open is a new virtual machine. So let me go back and set my project again. And let's see if this will work, because this has been historically working. Next. I know this is not what you guys came to here to see, but little diagnosis. Oh, I see what it's doing. Okay. Let me just reload and anyways, let's see how our render's doing there. Okay, so we have distributed rendering, and we have a bunch of hosts already rendering. Each of these machines has, let me maximize that. Each of these machines has 2 P100s. All right, so right now I'm rendering on 6 P100s. And so this is pretty cool. But let me go and log in to a different machine. Let's pretend I'm another user. So this one is in the same, it's a totally different machine. It's got a P4 as a graphics card instead of, or as a GPU instead of a T4. And let me authenticate there. And what I'm going to do, we're going to wait for this to connect, is I'm going to render a completely different scene. Now notice, by the way, in that other scene, this is actually a scene from Paul DeBevic's group. They've got some an HDR camera rig in here, which is really, or sorry, a light field camera rig in here, which is really cool. So this is like an animated robot. And also, yeah, the latency is actually pretty good. Like I can scrub around pretty easily here. Oops. And let me just zoom out a bit there. Zoom in. Okay, so I've also got, oops, I've got to launch the tool here. So now I can also request a bunch of IPs for this guy too. And this, you'll see these IPs are totally different, but we'll look in a second and we'll see the fact that they're running on the same hosts. So now I can go and leave distributed rendering is on in this scene. Yes, it is. And this one is using GPUs as well. And let me actually show you that. Let me show you that video because the, and there's no sound, don't worry about that. Just go full screen here. So this actually shows you as I walk through, yeah, you could see I can log into one of those pods and I can start to list the, I could start to look at the output that the V-Ray server command is giving me. And you could start to track things like, you could log in and track GPU usage and stuff like that. I think here I log in and I can create a bash shell on there and I can actually run NVIDIA-SMI. Like, you know, these are very simple things. I don't have like high level control over them, but you could see the GPU is working and it's you know, performing tasks. So let's go back here. All right, so here we have a render that is a little bit dark, but it is, I wish I had a proper mouse. Let me just change the camera tool to the track tool. And, you know, I'm rendering on these 4 machines, even though I can, once it spins up more, that's another thing about Kubernetes clusters is that once you spin up a node, it could stay alive for a predetermined amount of time. And if nothing is happening on it, it'll shut down that node. So it's actually quite economical. But what's also making this quite economical is the fact that the more users I have on my Kubernetes cluster, the more economical it is because they're all sharing the same GPUs. Now, obviously, you want to figure out the point at which the performance starts to slow down, and you could track things in the shell to do that. But here I've got these 2 users, and they're both logged in as separate users. This is actually a different user ID than the other machine, and they're both sharing the same GPUs. And let's just have a quick look at what's going on here. And so we've got these machines, and I can go in and look at one of these machines in my cluster. There we are. And you can see there's 2 V-Ray. Let me make this bigger here. You can see there's 2. These are all the processes that are running on the machine. And there's 2 V-Ray processes that are running. So if I had a third user that was logged in, it would just be a third V-Ray user that's running it. So there's a lot of different configurations that we could talk about, and I'll go into a bit more in a second. And you can also set, you know, maximums. I'm still getting more IPs here as well, but you can also set maximum size of your cluster so that somebody accidentally types 100 nodes or 100 IP addresses. That's going to you know, throttle them and limit them. So in the 10 minutes that we have left, we'll try to keep everybody on time here. So this is what I was talking about earlier, just to help you understand how the structure works. And there's, like I said earlier, clusters, nodes, and pods, and you can think of those as sort of hierarchical. And the cluster exists in what's called a VPC, which is a network. VPCs can exist in any data center in any region. And within this VPC, you have your cluster. And the cluster can exist across, within the cluster exist multiple nodes. And note here, there's what's called a control node. And the control node is doing things like hosting the license server, and it's doing a bunch of monitoring, and it's controlling it's deploying the node. So the control node will always stay there. The GPU nodes, they come and go. But the GPU nodes, the nodes can also exist across different zones as well. So for each zone, you have to have a control node. If you're running in one zone, you only need one control node, and that's sort of deploying and managing all the GPU nodes. If we look at what is running in each node, so the control node, like I said earlier, it's running the license server. So every GPU node that spins up a V-Ray pod is going to talk to the license server, and it's going to get the license from there. I'm using online licensing, pay-as-you-go, blah, blah, blah. So it's super easy and efficient, but this machine obviously needs access to the outside internet, and you can control which machines have access to the internet within cloud. And then it's running a bunch of other monitoring, and there's this notion of what's called the pod broker. The pod broker is what's taking the user request for resources, and it's taking their username and it's assigning them a few different things in this GPU node. So here on the GPU node, the only thing that exists is the NVIDIA driver, and each iteration or each pod deployed for V-Ray server. And we saw earlier what's in the V-Ray server pod is just V-Ray and NFS utilities to mount the shared file system as well. In this case, I'm using something called an elastofile cluster, an ECFS, which is a shared cluster-based file system that I've mounted on my virtual workstation as well as on these pods. Along with all the config files for Terraform and Docker is a Python API that we wrote. There's a few different modules, a few different files as well, but the pod broker, like I said before, it applies, it takes the username and it returns a bunch of IP addresses so that you could poll the IPs. Go back to the pointer here. It also uses what's called a load balancer, so everybody talks to the pod broker through the same IP address. And the pod broker's job is to create or destroy replicas. We call them destroy, not terminate, but it can scale it up and scale it down. That's what it's doing. And then you've got the different Python interfaces for writing the XML. Basically, I'm rewriting this V-Ray DR list file, which is a really interesting and simple way of changing your distributed render workers, which I was happy to learn that if you just change the file while it's while Maya's running, and you just stop and start your distributed render, it'll just pick up the new workers from that list. So it's super handy. And then this allows you to scale the workers, and then this cluster UI is just what the little UI runs inside of Maya. It's very basic, and I make no apologies as to how minimal functionality it is, but again, it's just sort of an early iteration. How much does all this cost, you might be asking yourself? And obviously, these numbers are elastic and your mileage may vary, but what you're looking at today, if it were running in the US Central region, by the way, I did all these pricing costs based on a region in the US. It's a little more expensive in Europe because of VATs built in, but to run that virtual workstation, which has 24 vCPUs and a 200 gig boot disk and 32 gigs of RAM and a T4 GPU is about $1.31 US an hour. And that's based on an 8-hour day, 5 days a week. We've got this elastofile clustered file system. I think I've got about 5 terabyte shared file system, which works out to about $1.70 an hour if you run it 24 hours a day, 7 days a week for a month. There's different discounts you can get for sustained use discounts. The cluster itself, the control node costs almost nothing because it's just a tiny little it's a 4-core machine or 4 vCPU machine. But each GPU node, because they have 2 GPUs attached, that's a little more expensive at $2.39 an hour. So if you add more GPUs, it's going to cost more. So the total cost of ownership for what you're looking at here, like my cost, I mean, I'm paying for it, but the cost to run it is around $5.50 an hour to run this configuration as you see it with a single GPU node. Obviously, if you scale out your GPU nodes, to times 10, you're going to be, instead of $2.39 an hour, it'll be like $23.90 an hour. So obviously, factor that in. But then when you think about how that compares to an on-prem render farm, there's a lot of different calculations you need to make in those realms. All right. Wrapping up, there's some more things that we could think about. Didn't have time to build into this demo. Auto-scaling, like we were talking about earlier, auto-scaling is sort of an interesting problem because what if you wanted to be able to auto-scale this Kubernetes cluster, which is totally possible, based on things like GPU load, right? So the more, like let's say if every GPU node's GPU usage was at 100% for X number of minutes, add another node. And keep doing that until the GPU usage sort of load averages below 100%, which basically means that you've served all your users and you're scaling out properly. Like there's things that can be done to base, based on the number of users and what kind of requests you're getting. Obviously, this demo doesn't use preemptible nodes and GPUs, but you could do that to lower your pricing dramatically. So those are standard prices, not preemptible prices. Preemptibles are 80% off, or around 80% off. And then you can also do things like track your budget. This could be an interesting extension to how the cluster works, and that's, what if you're like a production manager or an office manager and you want to be able to see, which users are using this and how many nodes they've called for, and what is it costing you per second? You could even get that information. So you can get this, what we call this live burn rate. So you can have an idea of what this is going to cost you. And let's say your budget for the day is $100, right? And if you track your budget and if you track your costs throughout the day and it hits $100, boom, you just stop your cluster and you tell everybody, sorry guys, you've used up your quota for the day and we can't do any more distributed rendering. Or if you're under budget, you could pass on that budget to the next day and you could sort of bank your burn rate and do more work or spin up more nodes tomorrow. You can maybe even give artists control over that too, right? Like give them the ability to scale up and down the number of nodes, which is probably not a bad idea based on the laughter from the front of the room here. So don't give artists the control over it. You could have this centrally managed so that make sure that one person has oversight or a small group of administrators have oversight over how much to spend and how big the cluster is. And then finally, you could have things, advanced scheduling is something that's sort of very Kubernetes oriented. There's this notion of pod affinity and anti-affinity. And these are sort of complicated terms that explain how you can share resources and share pods across different nodes. What we've got going here is what's called anti-affinity, which basically guarantees that your pods will always run on their own node, right? So if I request 10 pods, it's going to spin up 10 nodes. Because it's only going to put one of those. It would be useless to put 10 pods on one node because that's basically, a bunch of pods using the same resource. But now that means that another user that comes in, they're going to request 5 nodes or something. Their 5 nodes will all be spread across those 10, right? So that means that everybody always gets their own pods that guaranteed to be on their own nodes. But obviously, the more users that access this cluster, the lower the performance is going to get because now you're sort of stuffing more work into the same amount of resources. So then you might want to auto scale up the cluster, scale it up and down. There is a lot of information here to learn, and obviously I don't have a solution that's published yet. Maybe check out my Twitter handle or the Cloud blog. We'll announce when we have something to share. Maybe Chaos Group can post it on their blog, or Chris Nickel, might post it on CG Garage or something if I'm lucky. But the virtual workstation that you saw, this QR code will take you to a tutorial to show you how to build that. There's a version for Windows, a version for Linux. It's pretty simple to set up. You don't have to use Teradici, but it is one of the components of that tutorial. 55 seconds left for questions. I'm sorry I went so fast, but a lot to talk about.